Hello everyone, so welcome to final lecture for week 3. So where we are learning for word representation, and today we will focus on cross-lingual representation, right? So these will be topics. So what is the cross-lingual word representation, and we will talk about various approaches like monolingual, cross-lingual, and so on. That how do we learn this cross-lingual representation? So first of all, what is the idea for cross-lingual representation? So we have talked about word representation. You give me data in one language, and I can learn representation for all the words in the vocabulary. Right? That is what we did in word took and glove. But many tasks are actually multilingual or cross-lingual in nature, like translation. You are given a source language input sentence, you want to translate into other language, right? And what happens? You may not have data across all the languages from the same in the same manner. So you may have lot of data in one language, but may not have sufficient data in the other language. Now that's where it becomes very important if you can learn in some languages that are high resource, that are a lot of data, and transfer it to other low resource language. Okay, so that way, even if you are not able to learn good representation by that data itself, can you transfer something from high resource to low resource already, right? And avoid so much data requirements for these low resource languages. Okay, so this is the idea. Can we save training efforts if you already have some good representation in one language or some languages, but not for others, and get a good representation, right? And this is like what you are showing is how a cross-lingual representation will look like, where like children in English and kinder in German, they would come very close to each other. So they would in the embedding space, they will be very close to each other. Like that is the idea that you want to do, because once you have that, even if you do not have good representation for other words, you would know that, okay, so that would be very, if you do not know for this word, let's say, you know this should have been very similar to the life word in English, right? So once you have put them in the shared space, you know the translation for life would have very similar embedding as the word life itself, and that can help you in getting good embeddings for multiple languages. Now the models that are used are they use various ideas for this. For example, you can do monolingual mapping. So that is a simple default method that, let's say I am talking about English and Hindi, so I can train in a monolingual method for English, I can train another method for Hindi, and I can have some way in which I can align, I can do a mapping between the representation space. From English to Hindi I can map, right? And that's why I can align. So there I do separately, I learn and then learn a mapping between them. You can also use some pseudo-cross-lingual, where you can mix the context of different languages and train an off-the-shelf word embedding method on this mixed corpus. So we'll see an example for this kind of method, where you can mix data across languages, right, and create a corpus which is like multilingual by design. Then you can also do cross-lingual training, where you can have some parallel corpus across languages, and you optimize some cross-lingual constraint between embeddings of different languages, right? And we will see some examples for that. And you can also do joint optimization, where you have some parallel data, but you also have some monolingual data, and you jointly optimize some loss function that will be a monolingual loss plus cross-lingual loss. So this is another kind of methods, and we will see examples for all different kind of methods. And of course, in the literature there are they have so many works that have happened on learning this cross-lingual representations. Now, what is important to note is what kind of data would I need, right? And this data may vary, the requirements may vary depending on the method. So some methods would require very expensive data, and some methods will require very little additional data. Like the word aligned data, this is the most expensive, because what you need here is a parallel corpus between pair of languages and even with word alignments, right. So, this is very expensive. You need parallel sentences, also word alignments. It makes it easier to learn the embedding, but getting this data is very difficult. Then the slightly less expensive is sentence aligned data, where you have a parallel corpus between languages without word alignments, right. You may get some machine translation training data where the sentences across two languages are aligned. Even less expensive is document aligned data, right. So, where you have documents in different languages and you have topic alignment between documents. Like in Wikipedia, you may have a document about earthquake in English and a document about bhukamp in Hindi. So, they are topic aligned, right. The sentences may not be directly aligned, but we know that they are talking about the same topic. Or you can have the label or class aligned. That is another interesting thing, that is, it may happen that in sentiment analysis you have, this is the positive examples. So, positive examples in English, positive examples in Hindi or other language. You can use them to align, okay, the embedding. Or multi-class classification, where you have the same classes across data sets, but in different languages, you can even use that. Even less expensive is the lexicon. Let us say you have a lexicon, a cross-lingual dictionary, where for certain words this is the translation. So, you just know the pair of translations, even though you may not have any parallel data even at sentence or document level. So, even that can be used, or the final method is when you have no parallel data whatsoever, right. So, we will typically see various methods where you use methods from 1 to 4. So, let us start with the simplest of this, that is monolingual mapping. Okay. So, what is the idea? So, let us say, so here you have this again Mikolov et al. In their paper, this they had this notion that the word vector space can encode meaningful relation between words, right. And they also found that across languages this geometry holds, right. So, this is example for English and another language. So, this geometry was holding across languages. So, the question was that can we transform one language vector space into another language vector space, right. So, because see originally when you train them separately, what will happen? So, this so for language L1 and L2, so they will learn the representation where you can say, okay, pig and dog are connected, fine, but the vector for pig and in another language may not have a correspondence, right. So, because they are learned independently from some random initializations. So, even if you may have some connection between these two words in across languages, these two vectors may not have any connection, right. So, can we transform this vector space into this vector space, right, or can I take both of these to some joint space? So, simple idea that came is was that, okay, let us say I take some 5,000 or so most frequent words from the source language, and let us say in a dictionary I have a translation for these words. So, I have a bilingual dictionary where for these 5,000 words I have a translation from source to target, right. Now, what I can do, I say, okay, now each of these words, let us say a word xi in the source and gi in the target. I have the embeddings because they are already learned, the embeddings already learned. Now, I am just trying to learn a mapping, or I want to translate this embedding into this. So, what I will do, I will say, okay, I will multiply xi with a matrix W. Now, W can even take care of dimension. Let us say xi is from 100 dimension, zi is 300 dimension, fine. So, my W matrix will be 300 cross 100. So, when I multiply with xi 100 cross 1, I get a 300 cross 1 representation, right. So, now I am saying Wxi should be as close as possible to Gi, right. That is the mapping that I am learning, and this I can do over all the 5,000 or whatever number of words that I have mapping available for, and find out the best possible. So, minimize that and find the best possible W, and you can use gradient descent and other kind of methods for learning this mapping. So, that is a very straightforward method. Now, Farooqi and Dyer, they proposed a method that is a slight different from that. That is, they used canonical correlation analysis. And what they will do, so let us say I have two different, so this is two different embedding spaces. Okay, so for two different languages, they may have different dimensions altogether. So, what they will do, they will learn this canonical correlation analysis. They will learn a transformation matrix for each language. So, let us say I have this one matrix V and W. So, using this, what I will do, so I will get a representation in language 1, language 2. Now, you have the same dimension, and so I started from this, and I have got into sigma star and omega star, and you can see them as the same embedding space, that are shared embedding space. So, then rather than going from here to here directly, you take both of them together to a new embedding space, right, and then this is the embedding space where the languages have shared representation. So, this was the method that Farooqi and Dyer had proposed, that also gives a nice projection based analysis for cross-lingual representation. Now, there are some methods that are pseudo-cross-lingual. So, this is again a very nice method from Wulick. So, what they did, so you have some pseudo aligned data set. So, like you can take Wikipedia and you have article in 2 different languages on the same topic. So, what they will do, they will concatenate these documents, so that are on the same topic, and then shuffle them, so that the words across language are mixed. So, you shuffle them by randomly permuting the words. So, what will happen, let us say blue and the gray denote 2 different languages. So, what will happen in a context window, you may get words from different languages. So, given, and you can then apply same default method of word to X. So, what will you do? You will take a word and try to predict the neighboring words, and because the neighboring words can be in any language, you will learn the joint representation where a word in one language can predict a word in another language, right. So, you will get this bilingual context by this shuffle and merge, and it will get you a robust embedding space, right, where words are aligned across languages. We can also do cross-lingual training. So, like Herman and Blunsom, that what they did, they trained models to produce sentence representation of aligned sentences in 2 languages. So, for example, let us say you have 2 different languages, and the sentence here has 4 tokens, A1, A2, A3, A4, and here you have 3 tokens, B1, B2, B3. So, what they did, so they composed the vector representation. So, let us say they have embeddings, they use some simple sum of the embedding of words, right, in the corresponding sentence. So, let us say you have W of B1, W of B2, W of B3, the embeddings for 3 words. Now, you simply sum them over, call it the word representation. Similarly, you sum the 4 embedding of words and get the sentence representation, and then you say fine. So, they should be very close. So, they use the distance between the 2 sentence representation as the objective. So, they are parallel sentences. So, their representation should be very close to each other. And how do you get the representation? By taking the mean, the sum of the embeddings of the individual words, and use that to learn the good representation for the words, because these words will be shared across many sentences, and you will know, okay, if this word should have a representation very similar to another word, if they are coming together in many sentences, right, many parallel sentences. So, that is the idea. You can start from scratch without any prior knowledge of embeddings, but by this sentence alignment you can learn the shared embedding space. Another method from Lawley et al. So, what they did, they tried to reconstruct the target sentence from the original source sentence. So, let us say I have the same sentence in 2 different languages. So, what they did, so they started with a monolingual autoencoder. So, when we were learning word and embeddings, it was like an autoencoder when you have one word, but you were predicting the surrounding word. So, here what they will do, so let us say we have these 4 words, and you encode it as a sum of the word embeddings, right, very similar to the previous method. So, this is the encoding. So, encoding is simply the sum of the embedding for all the words, right, of the source sentence. Now, in autoencoder what we do, we try to decode the same thing. So what they do, they can decode all the 4 words, right. So they can decode all the 4 words. So reconstruct the original source sentence means they will decode all the 4 words using this encoder, very similar to how we did in word2vec, right. CBOW and skipgram. So you have this encoding and you decode into the individual words, right. So they did that, plus they made use of the parallel sentence. So you have this sentence also. So you can use this autoencoder to also decode the parallel sentence words. So and the decoder was hierarchical softmax, the one that we had discussed in the third lecture for this week. So they opt for a tree based decoder, that is hierarchical softmax. So in the autoencoder they also augment with the second decoder that reconstruct the aligned target sentence. So they will now start reconstructing the target sentence words, right. So you have multiple objectives. So you start from one sentence, you encode it such that you can decode these words, and you can also decode the words of the parallel sentence, right. So the 2 trees will be different, but the same encoding would help you do that, right. So that means if you have an aligned sentence pair S1 and S2, you can train it with 4 reconstruction losses, right. You will take S1, encode it, and predict all the words of S1, predict all the words of S2 to different losses. Similarly, you can now use S2, encode it, predict all the words in S2, and also predict the words in S1. So they have 4 different reconstruction losses that they had used, right, and that is how they learned the representation. Now there are methods about joint optimization as well, like this bilingual skipgram from Long et al. So what they did, so they extended the skipgram to the cross-lingual setting, right, and the same skipgram objective they used as both monolingual and cross-lingual objectives. So what they will do, so in skipgram, given a word, we will just predict the surrounding words, right, in the window. So what additionally they did, so they have this source language and a target language. In this case, they also had the word alignment. They knew the aligned word in the target language. So we will also predict the aligned word in the target language. Okay. So and they will go vice versa. So they will given the context, and they will predict this word, or they can also predict the aligned word in the target language. And same, given this word in the target language, they can predict all the context words of the aligned word, right. So they will predict all these 4 words. So they extended this skipgram model to bilingual setting by using the word alignment. So you have word alignment, just like you traverse using word alignment links to other sentence, and then start seeing the context of that sentence also as an extended context. So this was the idea. Similarly, this was a method from Ghosh et al. So this is a bilingual bag of words without word alignment Bilboa method. So that leverages both monolingual and parallel data. What is the idea? So let's say you have English and French monolingual data, and also some parallel data in English French. So individually on monolingual data, you can apply the word2vec kind of CBOW kind of method, that you have the context and you predict one word from that, right. You have a context, you predict one word. So this is very similar to your normal CBOW and skipgram. Additionally, what you will do, so you will take the parallel sentence, English and French, and there is no word alignment there, but you have the sentence alignment. So you will minimize the distance between the means of the word representation of the aligned sentence. So you have the English sentence, you have the French sentence. English sentence, you will take all the words, compute the mean representation. Again, from the French sentence, you will get the mean representation, and you compute the L2 loss, the distance between the 2 representation, after taking the mean, right, and they should be close enough. So this mean representation of the parallel sentence is a very interesting idea that many papers have used, that in the shared space, if you have parallel sentences across languages, they should have very similar representation. And this mean you can get by simply adding simply adding the representation, taking the average representation, and so on. And this can be used in addition to this monolingual laws like the one that you are seeing here, and that actually help them in learning much better shared representation for the languages. Now, Indian languages also there is a lot of work on producing the word representation. I'll just talk about one work that is recent, like Indic fastText, Indic FT. So this was proposed by AI for Bharat. So what so they had model for 11 Indian languages: Assamese, Bengali, English, Gujarati, Hindi, Kannada, Malayalam, and so on. And this is available for download. And this was just an extension of fastText model, but on Indic corpus. So they used Indic NLP corpus for learning the word representation. So, and I also wanted to show that because when we are doing this word representation, we need to have some way of evaluating how good they are. So evaluation can be done in two ways. You can do intrinsic evaluation, like intrinsically how good are the word vectors. So a good intrinsic evaluation is word similarity. So a lot of data sets are available where we know that these two words are similar and these two words are not similar, and this similarity typically is measured by humans. So you have various tests through which you give a pair of words to humans and find their similarity, and then you want to see if the embedding similarity is correlating well. So you find the correlation of the embedding similarity with the human rating of similarity, right? And you put some correlation scores, and higher the better. So they showed, for example, the fastText model that was learned on Wikipedia versus the Indic fastText that they had proposed. What is the correlation, right? So here, on an average, they were doing better than the original fastText model that also had this multilingual word representation. Another evaluation can be extrinsic evaluation, where you use this word embeddings for some task. Like here, they were doing it for a classification task, new genre classification. And again, for multiple Indian languages, they tried with fastText and the Indic fastText, and they found in this case across mostly all the languages, Indic fastText was giving a better performance for this task individually also, and average. So it was quite an improvement over the previous model using fastText. So this is another way of evaluation, that is you use them for some task, right? So for intrinsic, there are other evaluations also, like you can do analogy testing and so on, how good they are in analogy and so on, right? So yeah, I mean, this is a nice blog from where I have taken some of the content for this slide from Sebastian Ruder. So you can go through that for more details. And this also ends our week 3, where we had discussed about various word embedding methods and also some extensions. And we will use this idea in later lectures, where we would use word embeddings as a basic building block for denoting the sentence and higher units. Okay, thank you.